came to RIT fresh out of high school, from the farthest place we've ever gotten students before. That was Alaska at the time, right? To study, do her undergraduate degree in microelectronic engineering. And maybe she might have been like your classmate or somewhere around there.
I started 2002.
When did you start, Mike?
2001.
2001. And Monica spent a year with us, and she was in my lithography class, and she sat right up front on this kind of perspective over here. At the end of every class, or every class or so, she'd come up and we had a nice conversation. I looked forward to having Monica in more of my classes, but she went away a year after that. And I never thought I'd see Monica again. She did her BS degree in Portland, electrical engineering. And then lo and behold, a few years later, I heard from Mustafa Bushigar, who's the director of our PhD program, that somebody named Monica Kemskill wanted to come do her PhD in microsystems engineering and maybe do some lithography. So Monica came back. Soon after she arrived at RIT, I asked her if she wanted to spend some time in Belgium. So I sent her off to Belgium for a year and a half. She did great work with IMEC. What I didn't mention is before she came back to RIT, not only did she do her electrical engineering degree in Portland, but also spent a lot of time co-opting and doing internships at Intel. So she came back a real solid lithographer, spent a year and a half, about a year and a half on IMEC, and became even a better lithographer, and then was well on her way to do her dissertation for her PhD. So a lot of you know her. She's become a good sister to many of you, and a real sister to one guy right here is doing computer engineering. Good friend to others, a great student, and we already miss her. She's been gone for a few months now. She's just back today to defend her thesis, and then she's on to many good things back at Intel in Portland. So Monica, the rest of the time is yours. Now Monica's going to give a presentation for about 45 to 50 minutes. We're going to try to finish with enough time so we can have questions from the general audience before the hour. If you have a question in the middle of her talk, you can ask, but we're going to ask those questions and answers keep brief during her talk because we want to make sure she gets done. So if it's a clarification kind of question, certainly ask, raise your hand and ask. At the end, we'll have hopefully about 10 minutes for more questions. We'll ask you to leave at 5 o'clock, and then comes the fun where Monica gets to spend an hour with her committee members, and we'll ask her the real easy questions. Okay, Monica.
All right, thank you very much for that introduction. And I'll get right to it. The title of my dissertation is Pupil Wavefront Manipulation to Compensate for Mass Topography Effects in Optical Nanolithography. Just a quick check here. Bob, can you hear me?
Yeah, I hear you fine.
Okay, great. The semiconductor industry is driven by the downscaling of the integrated circuit. And lithography is a semiconductor fabrication process which uses near UV radiation in order to take a pattern from a mask and transfer it onto a light-sensitive film on the wafer called resist. And lithography has become the bottleneck of the semiconductor industry because it is required to continually provide higher resolution features as well as large process latitudes, or yield. As the features on the mask get smaller and smaller than the wavelength that's used to create that image, this sub-wavelength imaging can cause detrimental phase errors that are also referred to as mass topography effects, or thick mask effects, or three-dimensional effects. The objective of my dissertation is to increase the process latitude. And this will not only increase the flexibility of the design parameters, which includes the mask materials, or what materials can be used to create the mask, as well as the featured densities and sizes that can be successfully printed on the mask. An increased process latitude will also ultimately decrease the costs. My approach is to manipulate the parameters in the lens pupil domain of the lithographic stepper. First, I'm going to tell you what process latitude is. In order to calculate the process latitude, a focus exposure matrix, or FEM, is plotted with focus on the x-axis, which is the position of the wafer plane, CD on the y-axis, which is the critical dimension, or the width of the resist feature, and dose on the z-axis, which is the source intensity and time. In this simulated example, for a target CD of 40 nanometers and a plus or minus 10% CD specification, the acceptable dose values include 2 and 2.2 millijoules per centimeter squared. This can also be plotted with dose on the y-axis, focus on the x-axis, where the dose and focus combinations, which results in a CD which is within specification, lie within this blue curve. And this blue curve is called a process window. In order to calculate the process latitude, an ellipse is fit inside this curve, where the height of the ellipse represents the acceptable variation in dose, or the exposure latitude, and the width of the ellipse represents the acceptable variation in focus, or the depth of focus. A process latitude with a higher exposure latitude could also be found shown as the red curve. In this case, the exposure latitude is 10%. This results in a slightly degraded depth of focus for this example. I also want to point out that the best focus, or BF, is defined as the center of the depth of focus. The best exposure, or the BE, is defined as the center of the exposure latitude range. And in my presentation, when I refer to a depth of focus, I will be referring to one which has an exposure latitude of 10%. That simulation assumed an ideal mask. However, for sub-wavelength features, the assumptions on the ideal mask break down, especially when the width of the feature on the mask is less than the wavelength, and the thickness of the absorber on the mask is on the order of the wavelength. For an ideal mask, which is assumed to be one-dimensional, the electric field at the mask is a simple step function, where the clear portions of the mask result in a high electric field, and the absorber features on the mask represent a negative electric field, because for this example, the absorber induces a 180-degree phase shift. So this idealized electric field at the mask will refer to an electric field on the wafer, shown here in blue, and the intensity at the wafer, shown here in red. However, for an actual mask, the electric field is no longer a simple step function. Instead, the mask induces complex wavefront effects, which also could be referred to as errors, that could result in an electric field at the wafer that is out of focus, and an intensity at the wafer that has degraded modulation. It may seem that a simple solution to this problem is to simply shift the focal plane back in focus. However, the problem really comes in when you're trying to print multiple features, because the best focus becomes dependent on pitch. For this example, here I'm showing process windows. In yellow, I have a pitch of 90 nanometers, and in purple, it's a process window for a pitch of 120 nanometers, which is a slightly larger pitch. The corresponding best focus values are shown here, and the range in best focus, or the delta best focus, degrades the usable depth of focus over both features. So the goal of my project is to increase this usable depth of focus. So the first question I have to ask is, can the usable depth of focus be increased by using the mask and the source? So here I've done an optimization with parameters in both the mask and the source plane. I varied parameters on the illuminator using settings of a sigma center radius and a sigma center and a sigma radius that are defined there. And I simultaneously adjusted the biases for an 84 nanometer pitch and a 135 nanometer pitch in order to print at the same exposure. I then extracted the best focus and the depth of focus in order to calculate the usable depth of focus and the delta best focus. Here's a contour plot of the delta best focus between a pitch of 84 and 135, with sigma c on the x-axis and sigma r on the y-axis. With a large sigma c and a small sigma r, the delta best focus has been reduced to 10 nanometers, which sounds great. However, when you look at the individual depth of focus for both 84 nanometer pitch and the 135 nanometer pitch, you see that with a large sigma c and a small sigma r, the delta best focus has been degraded to only 10 nanometers. So the usable depth of focus over both features has a degraded depth of focus of less than 10 nanometers. So a method is needed in order to decrease the delta best focus without degrading the depth of focus of individual features. So since manipulating the parameters in the mask and source did not solve the problem, an alternate domain must be explored. Here's a schematic of the lithography system, where the source provides the illumination, The condenser lens collimates the light, the mask produces the diffraction pattern, the objective system collects the diffraction orders, and then refocuses it onto the wafer. In my dissertation, I am exploring the phase of the wavefront in the pupil plane, which is referred to here as pupil manipulation, and it exists within the objective system. So this raises the question, what form of phase manipulation would be useful? In order to answer that question, first I'm going to review simulated pupil wavefront errors. Then I'm going to talk about my simulation and optimization, and then I will present some experimental wavefront correction with sphere collaboration, and then experimental wavefront enhancement with astigmatism, and then I will conclude. Here I'm plotting simulated pupil wavefront errors that are calculated as the delta in the phase of the zeroth diffraction order and the first diffraction order mapped through the normalized pupil radius at the location of the first diffraction order. For one-dimensional lines and spaces on an attenuated phase shift mask with an absorber of tantalum silicon oxynitride, for a pitch of 84, the corresponding pupil wavefront error is shown here as a function of the normalized pupil radius. And this is plotted at the location of the first diffraction order. Likewise for a pitch of 90, 100, 110, 135, and 180. This is mirrored within the pupil radius because the source is symmetric. So this is the pupil wavefront errors corresponding to the right pole and the left pole. This is also done for contact holes on an attenuated phase shift mask with a molybdenum silicon absorber. And the corresponding pupil wavefront errors are shown for pitches of 90, 100, 110, and 120. Because the phase errors from the symmetric source are both rotationally symmetric and only vary along the radial component, they are similar to the fingerprint of spherical aberration. Here I'm showing primary spherical aberration, or Z9, and here is secondary spherical aberration, or Z16. This suggests that the pupil wavefront errors could be approximated using both primary and secondary spherical aberration. For the one-dimensional lines on the tachyon mask, the pupil wavefront errors have been approximated, shown here in green, by a wavefront that has both negative Z9 and negative Z16. This suggests that applying a wavefront that has both positive Z9 and positive Z16, this wavefront could compensate for the mask topography errors. For the contact holes on the MOSI mask, the wavefront is approximated with, in red, positive Z9 and positive Z16, which suggests that a wavefront with negative Z9 and negative Z16 could be used for compensation. Does it make sense that spherical aberration is the appropriate aberration used to compensate for mass topography effects? Well, spherical aberration is defined as the variation in best focus as a function of aperture. Here, this lens with spherical aberration results in a different best focus for rays going through the outer edge of the aperture versus rays going through the center of the aperture. And this results in a delta best focus. For a simulation done with a positive amount of spherical, Z9 equals positive 0.3, applied within the lithography stepper, this results in a pitch-dependent best focus. On the y-axis, I have nils, or the normalized image log slope, and this is proportional to the exposure latitude. So the maximum represents the best focus. And because this best focus is dependent on pitch, shown in the z-axis, this results in the delta best focus. So since spherical causes similar phenomena that is seen in mass topography effects, it makes sense that it could be used for compensation. Previous work has been done on pupil wavefront manipulation. A group in the Fraunhofer Institute at Germany with Professor Erdmann used simulation of a binary mask with an 80 nanometer chrome absorber illuminated by a dipole in order to decrease the delta best focus between a pitch of 90 and a pitch of 125. They reduced the delta best focus from 42 nanometers to 20 nanometers by applying a wavefront that has both primary, secondary, and tertiary spherical aberration. A group at ASML has presented experimental data on a thin attenuated phase shift mask illuminated by a dipole, where multiple features through pitch, both horizontal features and vertical features, using pupil wavefront manipulation, the delta best focus was reduced from 34 nanometers to 20 nanometers. In my dissertation, I am extending the experimental work on one-directional patterns to more complex two-directional patterns, and I am also extending it to thicker phase shift masks, both attenuated phase shift masks as well as alternating phase shift masks. Next, I'm going to talk about the simulation and optimization. I've simulated a variety of test cases, including a binary mask with a 73 nanometer chrome absorber with one-dimensional lines and spaces, a thin attenuated phase shift mask with a 68 nanometer molybdenum silicon absorber, both one-dimensional lines and spaces, as well as line ends. Both of these masks were illuminated with a Y-polarized dipole with sigma settings with an inner sigma of 0.595, an outer sigma of 0.928, and an opening angle of 40 degrees. I also simulated two-dimensional contact holes on that same molybdenum silicon mask, as well as one-dimensional lines and spaces and line ends on a 1% thick attenuated phase shift mask with 34 nanometers of tantalum under 113.5 nanometers of silicon oxynitride. These were both illuminated with an XY polarized C-quad, where the sigma settings were 0.66 inner sigma, 0.86 outer sigma, and a 30-degree opening angle. I also simulated an alternating phase shift mask, which has 171 chrome etched into the substrate, which has one-dimensional lines and spaces. This is illuminated with a conventional XY polarized with a sigma of 0.3. Simulation was used in order to find wavefront solutions that compensate for the mass topography effects by integrating MATLAB with ProLith, which uses the rigorous coupled wave algorithm in order to rigorously solve Maxwell's equations. Because the applied aberrations induce very large best focus shifts, the simulation needed to be robust through a large focal range to prevent errors such as image inversion and placement error. So the following procedure was used. First, I found the largest focal range where the nils was greater than 0 for multiple features. For example, both the right and the left sides of a line in an alternating phase shift mask. Then I found the best exposure at the focus which had the maximum nils. Then I performed a focus exposure matrix with broad values of exposure around the best exposure and through the entire range of focus where nils was greater than 0. I then iterated through a couple smaller FEMs until I had a smaller FEM where the exposure was centered around the best exposure and the focus included only the range of depth of focus. I then imported these focus exposure matrices into ProData in order to extract the usable depth of focus. For example, the usable depth of focus between a line, a space, and a shifted space on an alternating phase shift mask.
Oh, Bob, follow me.
He has slides. Bob, are you able to follow me okay?
Yeah, I know. You're on slide 15.
Yeah, let me know if you get lost. He's got the presentation mode and everything. Because each of those computational rigorous simulations are very expensive, an optimization algorithm was needed in order to optimize the parameter space while limiting the number of simulations. I developed an algorithm that's an evolutionary algorithm that takes place in 4 major stages. The first stage is the initialization, where I defined the candidates within set ranges, first on a Cartesian grid, 3 by 3 by 3 for primary, secondary, and tertiary spherical aberration. Here I'm showing it in 2 dimensions just for illustration. I also defined some candidates on a random grid. This was done on a grid of 0.01 waves, which represents the desired precision. In the assessment stage, I used a merit function of either the usable depth of focus, where the algorithm operated to maximize, or the delta best focus, where the algorithm operated to minimize. For each iteration, in the selection procedure, the 5 best candidates were selected to use as parents. For example, let's say this is one of the parents from the first iteration. In the modification stage, 8 children were created from each parent. First, this was done in a non-random manner by adding a 1 grid value, or 0.01, to each parent. This made the algorithm operate as a local search or hill climbing algorithm. So for the first iteration, this would represent the 8 corners around a cube of that parent, and in red they are shown as the children. Then the assessment stage would repeat, and again, the selection, the 5 best candidates were selected to use as parents in the second generation. Let's say that this is the second parent right here. So in the second iteration, instead of regenerating all 4 around the cube, this one has already been generated. So instead, a candidate to the side of the parent is generated. And each iteration continues until all children around the best parent are generated, and then a random value is added to each coordinate of the parent when all the adjacent candidates have already been calculated. The way this algorithm works is it uses both exploitation and exploration to optimize the parameter space. Now I'm going to show you some analysis of the solutions I found with the contact holes. Using a metric of usable depth of focus, I found many solutions that are limited by the pitch of 120 because its depth of focus was the smallest. The depth of focus of the pitch 120 is shown here in blue. And this solution, which has a negative amount of primary sphere collaboration, but 0 secondary and 0 tertiary, has a usable depth of focus of 115 nanometers. But the depth of focus is still the delta best focus is still rather large at 35 nanometers. However, using a metric of delta best focus, this led to the best solution because you can see that the process windows are much more aligned with a delta best focus of only 2 nanometers. By looking at the delta best focus as a function of spherical coefficient Z9, Z16, and Z25 for all of the candidates that were evaluated, I found that acceptable primary sphere collaboration was found in the range between minus 0.9 and minus 0.5, where this solution here is circled in red. The secondary sphere collaboration converged to a value of minus 0.12, where the solution here is shown in red. And the tertiary sphere collaboration was found to be acceptable when it was very small. Here's the solution for the one-dimensional lines on the Tachyon mask, where the solution is positive Z9 equals 0.05 and Z16 equals 0.08, and tertiary sphere collaboration is 0. Note that the solution is positive Z9 and positive Z16, which is consistent with the simulated pupil wavefront errors that predicted a positive Z9 and positive Z16 for compensation. For the contact hole solution, the solution is minus Z9 and minus Z16, which is again consistent with the simulated pupil wavefront errors. Experiments were done in order to validate the optimized solutions, and these exposures were completed at the University Microelectronics Center in Leuven, Belgium, using an ASML full-field immersion scanner operating at a wavelength of 193 nanometers and a 1.35 numerical aperture. Both yield star scatterometry and scanning electron microscopes were used for measurements. The induced aberration offsets were first using an image tuner on the 1900i, which uses lens actuators in order to produce low-order Zernike terms. And then I used FlexWave on a 1950i. The FlexWave has an optical element near the objective lens, which is made up of a grid of conductive and resistive structures. Each structure has an individual heating control, which allows unique aberration fingerprints to be created up to Z64. The FlexWave system is capable of producing aberrations that are 4 times the magnitude of those created by the image tuner. I also performed Elias aberration measurements, or integrated lens interferometer at scanner, in order to verify all wavefronts that were applied. Here's the characterization of the FlexWave system. In order to measure the repeatability, I performed 3 tests at 3 different locations: the center slit position, the 3 center slit positions, as well as measuring all 12 slit positions. Here's the coefficient in waves from Z5 to Z64. For a measured application of Z5 equals minus 0.1, you can see that the Z5 is very close to minus 0.1 in all 3 tests. The higher order spherical aberrations are all less than 0.004 waves. The flux wave system is also accurate in producing an offset with multiple coefficients. For example, a Z9 of positive 0.02 and a Z16 of positive 0.06. Again, all other Zernike polynomials are less than 0.004 waves. In order to maintain the accuracy, all wavefronts that I have applied have been measured and confirmed by the Elias aberration system. I experimentally evaluated a variety of test cases as I discussed in the simulation section, including the binary mask and the Mosey mask illuminated with the Y-polarized dipole. The reason why I chose this Y-polarized dipole is the diffraction orders allow me to probe the pupil differently for both vertical lines and horizontal lines. The diffraction orders for vertical lines are distributed along the radius of the pupil, whereas they are distributed along the edge of the pupil for the horizontal lines. I experimentally evaluated the 2-dimensional contacts on the Mosey mask and the 1-dimensional lines and spaces and line ends on the Tachyon mask illuminated by the C-quad, and the 1-dimensional lines and spaces on the alternating phase shift mask illuminated with the conventional illumination. All the lines and spaces on the binary mask, the thin attenuating phase shift mask, and the thick attenuating phase shift mask were biased through pitch in order for all of the pitches to print at the same exposure. However, the targets were set as drawn for the alternating phase shift mask in order to evaluate the usable depth of focus between a shifted and a non-shifted space for a given pitch. First, I want to show you some 1-dimensional lines and spaces on the thin mask, both the binary and the Mosey mask. Here I'm showing the process windows for multiple pitches, and the usable depth of focus is shown in red. You can see that there is a delta best focus observed through pitch. However, this delta best focus does not degrade the usable depth of focus, since it is only limited by the feature which has the smallest depth of focus, or in this case, the feature with the largest pitch. This implies that the 1-dimensional lines and spaces don't need wavefront correction, since they don't have a limited usable depth of focus. Because of this, it has resulted in a trend of thinner masking layers. However, this makes independent tuning of attenuation and phase difficult. So in my project, I'm exploring thicker masks because mass topography compensation can allow for the applications and advantages of these thicker films. So next I'm going to review the experimental wavefront correction using spherical aberration, first on lines and spaces of a Tachyon mask, and contact holes on the Mosey mask, and then lines and spaces on an alternating phase shift mask. Here I'm plotting the experimental best focus as a function of Z9, as well as the simulated best focus as a function of Z9 for multiple pitches, 84, 90, 100, 110, 135, and 180. And this is on the Tachyon mask. The simulation does a good job of predicting the pitch-dependent slope. Using only Z9, the delta best focus can only be reduced from 64 nanometers to 45 nanometers, which suggests that a higher order spherical term would be required for further compensation. I want to point out that the slope of best focus as a function of Z9 changes sign at about a pitch of 110. For 84 nanometers, the slope is positive, shown in red. And for 135 nanometers, the slope is negative, shown in orange. So this raises the question, why is there a slope switch? Well, the spherical effect is defined by the phase error between the 0th and first diffraction orders, because those are the ones that contribute to interference. For a source pole at a sigma of 0.76 and a pitch of 84, the 0th diffraction order is shown here as a function of normalized pupil radius, and the first diffraction order is shown in red. For a primary spherical aberration of Z9 equals positive 0.1, the phases induced on the 0th diffraction order are shown at this intersection in green, and the phase induced on the first diffraction order is shown here in red. Because the induced phases are radially symmetric, they can be perceived as a defocus aberration. Since first order defocus is modeled as a quadratic, the fitted quadratic's coefficient becomes proportional to the best focus shift. So for this pitch of 84, because the fitted quadratic term has a positive coefficient, that means that the applied aberration induces a positive best focus shift. However, this is different for other pitches because of the different radial location of the first diffraction order. Again, the radial location of the first diffraction order for pitch 84 is shown here in red. However, for a pitch of 90, it's shown here in pink. It also results in a positive quadratic coefficient, however, it is smaller. It's also positive for a pitch of 100. However, for a pitch of 110, quadratic now becomes negative, which is the same for a pitch of 135. This means that for a pitch of 135, the same applied aberration will induce a positive coefficient, a positive best focus shift on 84, but a negative best focus shift for a pitch of 135. So this explains why the slope of best focus versus spherical coefficient is the opposite sign for pitch 84 and for pitch 135. It's also negative for pitch 180. Using that previous model, I predicted the best focus shifts due to applied primary spherical aberration, and then I computed the slope of best focus as a function of Z9. And I found that it is proportional to this expression here, which is dependent on the fingerprint of primary spherical aberration as defined by a Zernike polynomial, where R0 is the radial location of the 0th diffraction order, or sigma, and R1 is the radial location of the first diffraction order. Plotting this analytical expression, best focus versus Z9 slope on the y-axis and pitch on the x-axis, the analytical expression is shown in blue and the rigorous simulation is shown in red and the experiment is shown in black. Note, for both the analytical expression and the rigorous simulation, the slope crosses zero between a pitch of 100 and 110. This shows that the analytical expression can provide some fundamental understanding about what's going on with the spherical aberration effect, but it only requires two computationally expensive rigorous simulations. The first computationally expensive rigorous simulation is done in order to find the best focus offsets with no applied wavefront, and then the second rigorous simulation is done in order to find the proportionality constant. I applied that model to the data on the thin mass for both horizontal and vertical features. For the vertical features, the experiment is shown in dots and the simulation is shown as lines. Note that the slope of best focus versus Z9 is pitch dependent. And this is because the vertical features diffraction orders are distributed along the radius of the pupil, so they probe the radially varying spherical aberration. This is confirmed by the analytical model, where the pitch is dependent on, the slope is dependent on the pitch, and it also shows a negative slope consistent with the experiment and the simulation. For horizontal, again, the experimental is shown as dots and the simulation is shown as lines. In this case, the slope is much less dependent on pitch. And this is because the diffraction orders are distributed along the edge of the pupil, where spherical aberration does not change very much. Again, this is confirmed by the analytical model, which shows much less dependence on pitch, and it also confirms a positive slope seen in the experiment. So this shows that the experimental model is able to replicate the experimental best focus trends, both seen through pitch and through orientation. Now going back to the one-dimensional lines on the Tachyon mass, in order to find the applied wavefront correction for compensation, this is the procedure that I used. First, I calculated the best focus as a function of Z9 and Z16 using the following expression, where the best focus of 84 is given as the best focus with no applied offset plus the slope of best focus versus Z9 multiplied by the Z9 coefficient plus the experimental slope of best focus versus Z9 multiplied by the Z16 multiplied by the Z16 coefficient. Here's the contour plot of the interpolated best focus of pitch 84 with Z9 on the x-axis and Z16 on the y-axis. This was done for all pitches all the way up to pitch 180, where the expression is shown here and the contour plot is shown here. Note that because the slope of best focus versus Z9 and Z16 is pitch dependent, these contour plots look very different. I then calculated the delta best focus as a function of Z9 and Z16 using the following expression, where delta best focus is given as the range of best focus over all pitches, 84, 90, 100, 110, 135, and 180. Here's a contour plot of the interpolated delta best focus, where Z9 is on the x-axis and Z16 is on the y-axis. The solution was where the delta best focus is the minimum, which is shown here with a Z9 coefficient of 0.02 and a Z16 coefficient of 0.06. This can also be done using the analytical slopes from the analytical expression, where this is the analytical slope of best focus versus Z9, and this is the analytical slope of best focus versus Z16. Here's the contour plot of the delta best focus, and the minimum is found with a primary spherical aberration coefficient of 0.02 and a secondary spherical aberration coefficient of 0.04.
What's the color bar mean? That's the delta best focus?
This is the delta best focus, and this color bar is the same scale for both plots.
So we get 0.
Well, the smallest blue is, yes, the smallest value is going to be like 0.01 or something very close to 0. Yeah. And that's where the solution is. It's where the delta best focus is the smallest. So this shows that there's good matching between the solutions found with the experimental slopes and with the analytical slopes. So I'm going to show you the process windows before and after the applied wavefront correction. With no applied offsets, the delta best focus was 64 nanometers through pitch, and all the pitches are 84, 90, 100, 110, 135, and 180. The usable depth of focus at an exposure latitude of 10% is 59 nanometers. With the applied wavefront correction of Z9 equals positive 0.02 and Z16 equals positive 0.06, the delta best focus has been reduced to 12 nanometers, and the usable depth of focus has been increased to 108 nanometers. This is an improvement of 83%.